Okay, here we're going to illustrate a problem or how to approach the solving of a problem in thermodynamics, right? So, as I said in class, we need to go through at least 3 steps. One is the representation of the problem, meaning that we show understanding of what the problem is all about. Then sort of formulating a plan to attack the problem. And finally, we should carry out that plan. And the outcome of carrying this out is getting the answer to the problem. So, in particular, we're going to focus on a problem where we have a mixture of two gases, hydrogen and oxygen, under some initial conditions. So, we have here hydrogen and oxygen at some initial conditions. For that, we need to identify its initial state. Right? And at some point, after the process, after this system is passing through a number of steps or processes, we will end up with what we call a final state. Right? In this final state, the only thing that is present in terms of these two gases is oxygen. Right? So hydrogen is no longer in the final state of the system. Right? So the question that we are interested in is in determining the initial composition of the mixture. In other words, the mole fraction of hydrogen and oxygen present in the initial mixture. Right? So, things to consider. What is the system we're dealing with? Well, the system is being represented. The system is a gas mixture, and we're going to represent that as an ideal gas system. And why is that important? Because by recognizing that it is an ideal gas system, we should be able to come up with the equation of state for that system. For an ideal gas, the equation of state is given by the ideal gas law, PV equal nRT, right? So, from this initial state, we know that there is some pressure, some temperature, and some initial volume. For the final state, we learn that the pressure is the same as in the initial state, temperature is the same, but then we have a different volume, F, final volume, right? So the question is, what has happened as you go from this initial state to this final state? When you read the problem, you see that this mixture is passed through a system that contains copper oxide, right? So when this happens, hydrogen will reduce copper oxide into copper. And liquid water. There is a reaction going on between this mixture and the copper oxide. The species reacting are copper oxide and hydrogen. So a reduction reaction takes place, and you still have oxygen that did not react. So here we have oxygen. The oxygen that is present will then reoxidize this copper to form back copper oxide plus, okay, copper oxide is the major product there. Things to consider. this hydrogen reacts with copper oxide, producing copper and liquid water. So what is also part of this component here is the oxygen that we have initially. Now, this oxygen will reoxidize the copper, forming copper oxide and some remaining oxygen, the excess oxygen. Because of the liquid water that is there, this oxygen is going to be wet. So, passing through this drying agent, will remove that water vapor from the oxygen, so you end up with just pure oxygen at the end. So, by looking at this process, we understand that oxygen is in excess. Hydrogen is like the limiting reagent for this process. Hydrogen reacts with this fully. There is no more hydrogen present here. All you have is oxygen that did not react with this copper. So the idea is to use that information to determine what is the initial composition of the mixture. So what can we do? Well, using this ideal gas law, we find that this relationship holds. Right? P over RT times VI is going to be N, and I will call N total, means the total number of moles of hydrogen and oxygen initially present, or present in the initial mixture. If I apply the same equation, but for the final state, right, then I will have P over RT BF, it's going to be N O to F. It's going to give me the total number of oxygens that remains after this process. Okay? So, since we are interested in mole fractions, that means part over a total, it seems natural to consider the ratio between these two moles, the number of moles of oxygen at the very end, divided by the total number of moles at the beginning, as a way to find ratios. So, if I now kind of make a connection here, in which number of oxygens at the end, or total number of moles of gases in the initial mixture, is going to be equal to BF over VI. BF over VI, keeping in mind that P over RT will cancel with P over RT because they are the same values in the initial and final state. So the claim is that we should be able to arrive or to connect the number of moles of oxygen that remains in the final state to the number of moles of oxygen at the beginning and the number of moles of hydrogen at the beginning, right? Or at the initial state. Well, NO2F should be equal to the number of moles of oxygen that you have originally. Let's use the I for initial state, minus the number of moles of oxygen that reacted. Let's use R for the number of moles of oxygen that reacted in this state or stage of the process, right? So if we use this information back into this initial equation, then you will see that BF over VI is equal to NO2I over NT minus NO2R over NT, This part here is nothing more than the mole fraction of O2 in the initial state. So that is now a relationship with this guy here. But then what would be the relationship between the number of moles of oxygen that reacted with the number of moles of hydrogen in the initial state? We need to find that out. Once we find it out, then we plug it back here, and then we see that it can be solved for the mole fraction of hydrogen. So to do that connection, we need to see what is the stoichiometry of the reactions involved. So let's take a look at that. The reactions. So then we're going back to this step. Reactions. Well, first reaction is copper oxide being reduced by hydrogen to form copper and water, liquid water. The copper that is formed will react with oxygen to form copper oxide. Now let's take a look at the stoichiometry. This equation is already balanced, but this one is not. To balance this equation, you can just use a half factor here, right? So now you see that the number of moles of copper is equal to the number of moles of copper produced in this step is equal to the number of moles of hydrogens present. And it's also equal to twice the amount, the number of mole of oxygens used for the reaction, for the second reaction. We call this reaction 1 and reaction 2 for the second reaction. So then we can say that this is equal to 2 times the number of moles of oxygen that reacted. This part here is this. This is the desired relationship because you can solve for number of moles of oxygen that reacted equal to the number of moles of hydrogen present initially divided by 2. Okay? So this term can then be used here. Right, so let's do it. This is going to be minus 1/2 the number of moles of hydrogen divided by the total number of moles, so that's going to be mole fraction of hydrogen. Okay, so far so good. If you want to be more explicit, you can do this. T minus 1/2 number of moles of hydrogen initially over NT. So that leads to mole fraction of oxygen, mole fraction of hydrogen. Okay. So I'm gonna erase this part so I can finish the exercise. Okay. Before I do that, then let's review what we just did. We know this is a key equation for us to find the answer, but we need to express the number of moles of oxygen in the final state in terms of the moles of oxygen in the initial state and the number of moles of hydrogen in the initial state. To do that, then we need the equations, the chemical equations associated with the processes here. And then we find that there are 2 equations, right? From this equation, we find the connection between the number of moles of hydrogen and the number of moles of oxygen that reacted. Okay, so let's now finish up. Okay, so this is then equal to XO2I. If I look at this equation, then you see that there is one equation and two unknowns. How do we go about it? Well, recall, right, that the mole fraction of oxygen initial plus the mole fraction of hydrogen initial is just equal to 1. Therefore, I can express the mole fraction of oxygen, or the hydrogen if you wish. Let's say hydrogen, either one. Hydrogen is equal to 1 minus the mole fraction of oxygen. Right? So then this portion of the problem will be 1/2 1 minus the mole fraction of O2 initial. Right? Okay. So then now it's a matter of algebra to solve for the mole fraction of oxygen here. So this is going to be equal to this minus, or actually plus, this times this is a plus, half mole fraction of O2I minus 1/2. Is that right? So, and this is equal to what? 3/2 mole fraction of O2 initial minus 1/2. So all we need to do now is solve for x, the mole fraction of oxygen in the initial state. So you can show that this is equal to BF over VI plus 1/2 times two over 3. These are quantities that we know experimentally, BF and VI. So all you need to do is plug those numbers in and realize that x of H2 initial is 1 minus x O2 initial. And then you will have solved the problem here. Right, so you may want to indicate initial and initial now. And that is what you need to do to approach the solving of this problem. Thank you.